Welcome. We're now in topics in the ring theory. We'll be considering some results. Topic is for the results in the theory of rings. Okay. First we begin with definition. What's a ring homomorphism? I'm sure now you are good at the definition for a homomorphism from a group G into another group. What if we have rings? We want to map from two rings into another ring. I believe you recall what a ring is from Maths 203. So a ring homomorphism is a map. This map and maps from a ring into another ring, such that if you pick any two elements from the ring R, it will satisfy this distribution. That is, if you take the sum A plus B and the map acts on it, it will break it into two to be the map acting on A on its own plus the map acting on B on its own. And the second identity is just like you're working with homomorphism of groups, where you have the product AB and theta acting on it, will split it into two different ones. So it's distributive over addition and same also over multiplication. And the third condition is that 1 theta equal to 1. I'm sure you still remember how to prove this identity. We want to show that 1 theta equal to 1 using the clue I had given both in class and in the previous videos. So in other words, theta respects addition, multiplication, and the identity element. So what now? The next definition you need to know is what we call a surjective ring homomorphism. I believe you know what a surjective homomorphism is. Another name for it is what? An epimorphism, right? Same also for rings. So a surjective ring homomorphism is called an epimorphism, while an injective ring homomorphism is called a monomorphism. Very similar to those of working with groups. Okay. Now, a ring homomorphism, which is injective and surjective, so both injective and surjective, and it's a homomorphism, is called an isomorphism. Okay, so meaning it is bijective, then it becomes an isomorphism. So the next definition you need to know is an isomorphism. So when do we have an isomorphism? So an isomorphism of a ring upon itself, so the ring is acting upon itself, is called an automorphism, meaning it's a homomorphism, it is injective, and it is surjective, and it is acting upon itself. So a homomorphism of a ring upon itself is known as an endomorphism. Did you see that part? It's acting upon itself, so it is an endomorphism. But if it so turns out that it's a homomorphism, it is injective, it is surjective, we then have an automorphism based on the fact that it acts upon itself. Okay. Now look at this definition. Now if we have a map theta which maps from the ring R to the ring S, being a ring homomorphism, you know what a ring homomorphism is. It is one that satisfies these identities, right? It's 3. Okay, so if it's a ring homomorphism, then 1, it's the kernel of theta. You remember what a kernel is? It collects all elements mapped to 1. A denoted kernel of theta is all the elements G that theta takes to 0, basically taking it to the identity. Okay, under addition, you know the addition 0 will be our identity, right? Okay, so the image of theta denoted in theta is all the maps, okay, of X, and where X are taken from the set of rings. The rings are, okay. So that's how to define the image. That's how to define the kernel of theta. Remember, theta is a ring homomorphism. Okay, so these are definitions you need to know. There are other information you might get in your lecture notes, but for now, this is what I present to you. Okay, so we go straight into what we call an ideal. So there are left ideals, there are right ideals, and then there's the ideal. Now, a subset. So if you have a subset of a ring, so you have a ring R, and you have a subset A of the ring. Okay, so this subset is called a left ideal. It's called a left ideal. That subset is called a left ideal if it satisfies these two conditions. 1, if you take any two elements A, comma B. Okay, in A, and you take A minus B, the result you will get will be again in A. And the second condition is that if you take A in our subset A and you take R from our ring and you multiply A on the left, watch, if you multiply this and the answer you get lies in A, then you say that A is the left ideal. Okay, so if these two conditions are satisfied, then A is a left ideal. So pick two elements from A, subtract them, you get results in A. Pick an element in R, the ring that A is a subset of, and an element in A, multiply it on the left, then you have, and if it's satisfied, then you have a left ideal. The next definition is similar. It's just that now it's the same subset, it's a ring, but now it's called a right ideal. It will, if it satisfies the subtraction, which we had shown before, but this time you're multiplying on the right. So you pick A from our A and then multiply R on the right hand side. There we have a right ideal. Now, if it is both a left ideal and a right ideal, we say it is an ideal. Let's take it up. So again, if it satisfies the fact that it's a left and it's also a right ideal, we say it is an ideal. So a subset A of a ring R is called an ideal if it is both right and a left ideal. Okay, let's continue now. The next thing you need to know is what we call the coset of rings. How do we mean? So let K be an ideal of a ring R. So we have K, an ideal of the ring R. This quotient, you say, denote all its elements take the form X in R ring and K, which are ideal, is the cosets of K in R. Then the definitions, the addition of two elements from this. So if you have this quotient, this is how the sum in its set goes. And if you have the subtraction of this, it's the same as taking the subtraction of X itself plus K, the ideal itself. And if you multiply two of its elements, it would look exactly like this. Do you know that? So basically, this is how to multiply, add, and subtraction element, the negative element in this particular quotient. This is how it takes its form. All its rules that governs it are so. So if I happen to give you any quotient and ask you to show me how the elements in that quotient looks like. So in our case for a group, we'll have the quotient G modulo N. Do you remember? Where N is a normal subgroup, okay? But in our case here, our normal subgroup for the ring is an ideal. Instead of the normal subgroup, we use ideals in rings and satisfies its identity. And this makes our modulo K into a ring called the quotient ring or residue class of R by K. So this property of it makes us it gives it a unique property that makes us call it a quotient ring or a residue class ring of R by K. Okay, let's move on. Now we want to consider an example here. Having known the definition of a right ideal, the left ideal, and what an ideal is, and you also know what the property of the quotient element will look like. And you know what a ring is, you know what a homomorphism is, automorphism, monomorphism, epimorphism, endomorphism, so all those phisms. So now we have an example here. We want to show that any set of this form, okay, these are basically multiples of any element in the set of integers, is an ideal. Clearly this is a subset, so there's a multiple of whatever you pick. Definitely this is a subset of this. Is that true? Set of integers. So multiples of integers and the ring of integers directly. Okay, so show that any set of this form is an ideal. So we need to show it is left ideal, so right ideal, and then finally find out if it is an ideal. So let's find out. Now we know what these elements in this set look like. They actually look like, so we let A to be equals to the NZ, because they're multiples of any element in the set of integers Z. So we pick X, and the take this form. So if it was 4n, it means the set will consist of elements of the form 4, 8, because I'm doing 4 times 2. Okay, let me show you. Let me show you how it looks like. So basically, you're doing something like n. That would be n4, right? N with 4, 4x, not n4, but 4x. So it will be like 4 instead of integers. It looks something like this. So this would be 4x, such that x is a set of integers, right? I know what elements are in the set of integers, so it could be something like this. You have minus 4, you could have 0, 4, 4 times 2, 8, 4 times 3, 12, and on. You understand? So those are the elements in this particular multiples, just multiples, a set of integers, okay? Since we didn't specify whether they're positive integers or negative integers, so it's the entire set of integers. Okay, so let's work on now. So it looks like this. Okay, we have to show that A satisfies the two properties, that it's the left ideal and right ideal, and then if it is both, then we'll know it is an ideal. Okay, so we start with the left side. So we picked two elements from A, right? If you remember when I was defining earlier, we had said that for it to be a left ideal, let's just go backwards and see. For it to be a left ideal, we had seen that it had to satisfy this property, right? For a left ideal, we pick A and B in our ideal A. For our case, it is N, Z, right? Okay, so we want to find out that if we pick any A and B in this set. So since we know the elements of this form, they're in the form of nx, right? So x, we have to be careful with that x. We will change it because there are two elements. So A could be n. You could decide to call it nx1, and B could be nx2. It's up to you. Just have to be careful with this x in your choice of values. It could be A to be equals to nx, and B could be equals to ny. Just be careful with the x part of it. Okay, let me clean this so that if we need to come back, we have the screen available for us to use. Okay, so let's move forward again. Okay, so we're here now. We're trying to show that this is an ideal, right? So we want to check for the left ideal side of it. So we pick A, B in A, and we need to check for A minus B, which is the first thing we should check, and then later we'll check the left part of it. So let's check the A minus B. So A and B in this will take the form nx, and B will be ny. Like I said, you could decide, you could make it to be equals to nx1, and B could be equals to nx2, depending on how you want your computation. But just being careful that the n remains n and these two are changing because there are any elements in the set of integers z. Okay, so now what will A minus B look like? It will just simply be nx minus ny, because A is nx and B is ny. So wherever you see, put nx, wherever you see B, put ny. Okay, so if you factorize, because we're working with a ring, we could factorize, remember? So n is common to both of them, that's why there's n out here, and you're left with x minus y. And obviously this number, this particular value, lies in a set of integers, right? So that will be true. Okay, so therefore we have shown that if we subtract any two elements in the set of integers, it will satisfy it will still be in A itself, where A is nz, a set of multiples of x. Okay, so now moving forward, we've shown that the subtraction works. We need to check for the left coset part, where we take A and multiply on the left by r. So we pick two elements, right? Okay, so same thing we do. Okay, we pick A and we pick r. Okay, remember that this is a set of integers, right? Okay, so whatever we pick in A is actually our this is what A is, right? So it means that if I pick a small letter a from that, my a will be something like a multiple of any element in the set of integers, right? So that's why you see it's still nx here, and I'm multiplying by r, right? So look at it there on the screen. You can see here that we multiplied on the right by the left by r, and by the time you factorize, because we're working with integers, right, you can factorize and the n comes in. This is just multiple of another value in the set of integers, right? Because r times x definitely will be in this. Why? Because r was taken from the set of integers, and so was x too, right? So that settles that, okay? And therefore we can conclude that it is indeed a left ideal. So we found out that it's a left ideal because it satisfies the first identity, that is a minus b is an a, and when you take the left multiplication, it is also in a, therefore it is a left ideal. So we've sorted that part of it. Okay, we're still on our way. We're to show that it's an ideal, not just a left ideal. So we need to do the right ideal part of it. So let's continue. Okay, so next we check for right ideal. That's what we have here. Again, we just simply need to do the second part of the identity. Let's check the definition for right ideal again. For the right ideal, we said it needs to satisfy these conditions, right? And this one we don't need to do again because we have done it in the left. So all we need to do is check for the right hand side. So let's go on and see what that looks like. Okay, so for the right hand side, again, we pick a, right? And we pick our r, right? And we have it as this because you know what a is, you know what r is, and multiplying on the right hand side and factorizing, you can see that this is, again, this xr definitely lies in the set of integers, and so n of it will be a multiple of that, right? So this also is an nz, and what's our nz? Nz is just our a, and so we've succeeded in showing it is a right ideal. So if it's a right ideal and a left ideal, what do you conclude even you for yourself? By definition of an ideal, once we have it is a left ideal, is a right ideal, we say it is an ideal. So now, since the set of multiples of integers in n is both right and left ideal, we conclude that it is an ideal. Okay, so with that, we conclude that part of the example. Now we consider a lemma. This is how the lemma goes. We're told that we have R, a commutative ring with identity. So the ring, it has an identity. Then R is a field. So if you want to remember what a field is, you might need to refer to your 203 lecture notes, okay? Then R is a field if and only if its ideals are the zero ideals and R itself. So we have an if and only if situation, meaning that we have a biconditional statement before us, right? So we need to prove both directions, okay? So we will need to accept that it is a field and then prove that it's an ideal with its only ideals are zeros and R itself, okay? Or we prove that we accept that its ideals are zeros and the R itself, and then prove that it's a field. So proving in this direction means we're going to accept that it's a field first and then show that the only ideals are zero and R itself. Okay, so we accept that it's a field. Okay, so if it is a field, it means that we can get a proper ideal R in it, because we want to prove that it has only zeros and the zero ideal and R has only proper ideal. So let's just it's only ideals. So let I be a proper ideal in R. So we're expecting the negation, right? So since the proper ideal, it means that it is not equal. It's just an ideal contained in R. It isn't equal to it. Okay. So since I is an ideal, what does that mean? It means the property A minus B will be in R I, right? Because that's an ideal, and it satisfies both the right ideal and the left ideal law, right? Okay, so both of them are in it. So okay, so let's read on. So if it's an ideal, it is an additive subgroup of R, and for any A you pick in R and B in R, it means that this A, B will be in I, right? It's a proper ideal. Okay, so we know that I is not empty. Okay, and so there exists an x in I, x not equals to 0. Now we said R is a field, right? Meaning that for all R in R is not 0. So there exists an R inverse in R such that this law would hold. Okay, as in I can multiply this because it's a field. It doesn't have any element 0, right? I can divide in it. Okay, so and this is going to be in I. Why? Because it's an ideal. It satisfies those conditions like we said earlier. Okay, so now but notice this. R can be written as R times 1, right? And R times 1 is in I. Okay, so it means that every R lies in I. And what we just said, that I is a proper ideal in I. Also, that is also possible because I is an ideal in I. It's an ideal in R, right? So now we can see that R is contained in I. And we already know, we said from the beginning here, remember what I wrote here? I just claimed it, so let's see. But from here, I is contained in R. And now R is contained in I. What does that tell you? That tells us that our R is equals to I, meaning that our proper ideal would definitely either be the 0 ideal and R itself, and you can see it here, and that is satisfied because once you have I contained in I, both containment and R contained in I, definitely it means that R equal to I. Okay, and that completes one direction of the proof. So basically you want to get a proper ideal first, confirm that that ideal is not empty, and definitely it isn't empty because it's an ideal properly, right? And then because it's not empty, you can find an element in it. And because R is a field, you can find an element of this form in it, and because there's this element in it, and you know that it's not empty for sure, you can multiply this to get 1 because this 1 is also in I, right? In R itself, right? But then R times R inverse gives us 1, and we know that this I is an ideal, so therefore this will lie in it because this is so. But then carefully note something. R is the same as R times 1, meaning that every R in our ring R, when multiplied with 1, will be in I. Oh, that means that R is contained in I. And by the containment, the fact that I is contained in R and R is contained in I means R is equal to I. And therefore, we've proved the second part of the first direction part of the proof. The second part of the proof now. So this is the opposite direction, that is conversely now. We want to accept now that the ideals are R and 0 itself. Okay, so we only need to show that it's a field. What do we mean now? Basically, you can find A and A in R, A not equals to 0, such that if you multiply any two elements in it, you get the identity. That was why we're able to do R times R inverse to give us 1, remember, in the other side, because that's what happens when you have a field. So we can pick two elements and get the identity, which is what we want to do now. Okay, so to do that, we first define a set. This set is defined based on the fact that I know R, okay, it's a ring. And because it's a ring, I can do some manipulation of this form. And I want to prove to us all that because R is a ring and every R is multiplied by some A, and A is actually an element in R, that it will be an ideal. I claim that. So that's why I'm claiming that RA is an ideal. So I'm going to prove the claim. So I check that this will be an ideal. How do we do that? Remember what we did? We picked two elements, A, comma B, in a given ideal, what we wanted to check to be an ideal, and confirm that A minus B was in A, and the left multiplication and the right multiplication was in A. When we checked all of that, we confirmed that it was an ideal. So we need to check that for this nice ring that I just defined. Okay, so let's see whether that will be true. So that's what we're doing on the screen here. So we picked two elements, X and Y, not A and B, because I have A hiding in my definition here, so I'm being careful with that. Okay, So it means that if I pick X in RA, I know all the elements look like this. So it's going to be R1 for X and R2A for Y. Okay, so you do the subtraction. Wherever I see X, wherever I see Y, I put my new values, these two values. So that's how I have this here and this here. A is common to both of them, so I can do this, right? And truly this lies in my set here because R1 and R2 are all from my ring R, right? They're from R. Okay, so that satisfies the first condition for A minus B. The second condition is to check that it's a left ideal, right? So for the left ideal, we'll take Rx, okay? So R from the ring and X from my defined set here. Okay, I want to show it an ideal. So you take a multiplication and this is what you have. Clearly this lies in here because R times R1 lies in my big R and A remains as it is. So it shows that it is actually, we've only shown for the left hand side. So you can do the right hand side. I just concluded here. So R8 is an ideal, not sufficient. You need to also check for XR. So everyone, ensure you check for X1, and even in the result, when you're submitting, if I happen to ask this during the exams or any test, ensure you do the right hand side, the right ideal part, because this is only for the left. So everyone should check for X, R, and confirm that you get an ideal proper. Well, it is an ideal, but make sure you complete the proof for that. Okay, so now it's an ideal. So now by our assumption, R has the 0 ideal and R itself is an ideal, so RA is equal to 0. So wait, our assumption is that we have that it's a 0 ideal, right? And the ring R itself is, I know we agreed, our assumption is the other direction. Sorry, I'm coming. So this is what we assume that the only ideals are R itself and the 0 ideals, and I've shown that this is an ideal. So if this is an ideal and R is an ideal, it means that this, my set, truly must be R, or that the ideal is the 0 ideal itself, okay? So, sorry, let's continue forward. Okay, so now by assumption, R has 0 ideal and R itself as ideal. So therefore, RA will be equal to 0, or RA must be R itself, right? Which is what I was saying. But what's this? 0 is not A, is right? So I can write A as 1A, and this will lie in RA. Is that true, everyone? Clearly it is so, because 1 would then lie in my R and A stays as A, right? So this is true. So we have that my RA, that set I defined, is actually R itself. Now, since 1 lies in R, our goal again is to show that AB equals to 1, because 1 shows a field, right? With A not equals to 0 and B not equals to 0, but basically that's what we want to do. Okay, so we have seen now that A lies in RA, right? And RA is equals to R itself. So we've shown that our ring is actually this. Now, since 1 lies in R, we have that there exists a B in R, such that BA will be equal to 1 and 1B equals to AB. How did we get that? From this our proof here, okay? So commutativity by the commutative property of R, okay? And the proof is complete. So basically what you've seen us do is first to define, for the second part, is to define a set RA. RA satisfying the fact that I can get another B in R, such that BA will be equal to the identity, and this will be same as AB. Why? Because it is both a left and a right ideal. Okay, so if you have any questions with the proof, you can ask questions on the WhatsApp group, and anytime we meet in class. Okay, so these are references, and thank you.